Hey everyone, welcome. Project 1. Project 1 is now available. We got it out Saturday afternoon, and so I put the due date a little later than I'd originally intended. It will be due 2 weeks after it was put out, so not this coming Saturday, but the Saturday after that at midnight is when Project 1 is due. It's a lot of work, so please get started early. Homework 3, which is due this Wednesday, is designed to give you practice on some of the skills you'll need to complete Project 1, especially the run length encodings in Project 1. There are handouts available that give you some of the code that we're going to go over in this lecture so that you don't have to copy that particular code down in a big hurry while I'm talking about it. So please pick up a handout if you haven't got one already. Today's first topic and main topic is going to be about where Java stores your stuff. And Java pretty much stores your stuff in two places called the stack and the heap. So we'll learn about those. They are both pools of memory, open-ended pools of memory. The simpler one is probably the heap, or at least the simpler from an outsider's view. And the heap is where Java stores every object. And arrays are objects, that includes all the arrays. And there's a few other miscellaneous things that get stored in the heap as well. One of them is class variables actually get stored in the heap in a special hidden secret container for the class. Remember, class variables are the ones that we declare static in a class. Then there is the stack. And the stack's job is to store all the local variables and a bunch of other hidden stuff. And it's worth remembering that the parameters you pass to a method are local variables. So this includes the parameters. Now, here's where things get interesting. When the Java virtual machine calls one of your methods, the Java virtual machine creates a stack frame for that particular call to that particular method and stores it on top of the stack. So the reason the stack is called the stack is because you pile up stack frames, one on top of the other, in this stack. Where'd it go? Probably there. Stack frames are also known as activation records. So if you ever see the word activation record around, that's what this means. And so that stack frame has slots where it stores all of the parameters that are input to the method and all of the local variables that are declared at any point in the method. Yes?
So you said that the heap stores all arrays and objects,
Mm-hmm.
also local variables.
Mm-hmm.
How distinguish you a quiz if you have an array created locally?
If you have an array created what?
Locally. If you create an array within some sort of local frame.
So if you create an array within a method, then when you construct the array with the new command, that array gets constructed on the heap, but there is a reference to that array as well, and that reference is on the stack. One way that Java differs from languages like C and C++ is you can't declare arrays on the stack. You can do that in C, you can't do it in Java.
What that means that if you, for instance, create an array,
Mm-hmm.
if you already have a reference of some kind outside the local frame,
Mm-hmm.
you create an array in the local frame, and then you bind the reference outside the frame to that array you created,
Mm-hmm.
it means the array will still be accessible outside that frame.
That's right. So you can create an array inside a method, return, say, a pointer to that array, or some other way make that array accessible to outside methods, and then it's still there and still available to other methods after that method returns. And so the Java virtual machine, again, maintains, as I said, an internal stack of stack frames. And in that stack, main is always at the bottom, because we always start with the main method, and the top of the stack is whatever method is executing right now. So I want to draw an example of this. So what I'm going to do is I'm going to divide my page into two sides, and everything on the left is going to be the stack, and everything on the right is going to be the heap. Now, what I'm going to do is I'm going to simulate a call to the insert end method in the slist class. So we're inserting a new item at the end of an slist. And stack frames are going to be built up starting from the bottom of the stack and building up. So at the very bottom of the stack, we're going to find the main method. So specifically, let's suppose I'm running test code in the slist class, and that test code is in the main method. Then that's where I start. That's the first stack frame on the stack when we start our program. And that stack frame will include space to store local variables, including the parameter. Every main method has a parameter called args, which you'll remember is the command line arguments. So args is stored in that stack frame, but the array of words that it points at, that's on the heap. That stuff is set up for you by Java as soon as your Java program starts. You don't actually have to write code to set up that. That's done for you when the main method starts. We also declare some local variables in the test code. So for instance, since I want to test out some lists, I'm going to have a variable where I store my slist, and I'm just going to call it list. But that variable, let's suppose that we make it point to a brand new slist. So the head is initially null, the size is initially 0. And then we call the insert end method, passing in a string. Well, I'm going to store that string in a local variable before I pass it along as well. Let's just call it str, and this is the string I want to insert at the end of my list. Now I call the insert end method on my slist, and when I do that, when the main method calls the insert end method, the Java virtual machine creates a new stack frame on top of the main stack frame for the insert end method. Now, since I called insert end on a specific slist, that slist gets passed in as a parameter called this. So the call was list.insertEnd. So Java automatically copies list into a variable called this, which is stored in the stack frame too. And that initially points to the same thing that list points to, because that's what I called it on. The insert end method also takes a parameter, which is the object or item that we want to insert into the list. So the parameter obj is a copy of the parameter we passed, str. Now, the job of insert end is to insert this string at the end of the list. To do that, we need to create a new list node to store that string in. So insert end is going to call the slist node constructor. And a constructor is just like any other method. It gets its own stack frame. And sometimes when you look at the stack dumps that you get out of Java when you do something wrong, you'll notice that constructors are labeled in that stack trace as slistnode.slistnode. And again, we will pass obj in as a parameter because we need to know what string to store in that brand new slist node. But the constructor will also do its job, which is to construct a brand new slist node. And so that slist node gets stored on the heap. And it has an item field and a next field. And when we first construct that object, it also gets stored locally in a variable called this in the slist node constructor method. And then that constructor copies obj into the item field. So now the slist node is pointing at the correct item. And it sets next to null. And so this is what the stack looks like just before the constructor finishes. Any questions about this? Mm-hmm.
More side question, but here I also have to take in, since string is being passed by reference, or whatever you want to call it.
Java doesn't have pass by reference. String is being passed by value. But it's the reference that's passed by value. I'll talk about that in a minute too. So the next topic of this lecture is pass by value. Question back there. Can you talk a lot louder, please? I can't hear your voice at all. Does slist main have access to all the local variables? So the way that the stack works is that only the method on top of the stack is running. All of the other methods on the stack are waiting for the methods above them to finish so that they can resume function. So right now, main is frozen and it can't do anything until all the stack frames above it go away. So main doesn't have access to those stack frames because those stack frames will be dead by the time main can run again. Yes?
So the order in the stack matters?
The order in the stack matters a lot. So the one on top, that's the one that's running right now. If that one ever finishes and returns, then that stack frame will disappear, and the next one down will resume running. If that one ever disappears, then the next one underneath that will resume running. So every method that's not at the top of the stack is waiting for all the methods above it to finish so that it can start running again. Does that make sense?
But what if you also have a method called insert before that is the order?
Well, you can't run insert before and insert end at the same time.
So when it gets called, it creates an item in the stack?
Yeah, when you call a method, it creates a frame on the stack, and then that one starts running until it returns, or calls another one. Question here.
So now there's a string variable called str in the main. What happens if you pass the string directly without declaring it?
Oh, you could have passed in a string directly without declaring it if you wanted to, sure. Well, in that case, if you had just passed in a string directly without saving it to a variable first, then this variable str just wouldn't be there, but the string would still be there, and it would still have a obj pointing to it. Question here. Is the volume too high? Down or up? Up. Okay. This is about as high as it goes, so I hope this will work. Question here. I'm going to avoid garbage collection for the most part until the end of the semester, but the main point is that nothing on the stack is ever garbage collected. Garbage collection affects the heap only. So that's the important thing. The gentleman way in the back there. On exams, I will generally give you instructions at exactly what moment in the code's execution I want you to draw the stack. And so that will vary depending on the problem. Mm-hmm.
If for some demented reason you wanted to change the order of the stack, is that possible, or is that on like a lower level of code that we're working with?
In Java, you definitely don't have access to move things around on the stack. In C, you can do crazy things like that if you know what you're doing, but not in Java. Java defends itself from that kind of thing. Mm-hmm. Primitive methods? You mean like a plus sign? Primitive operations like adding 2 ints never creates a stack frame. That's always done within one method. So as I said before, the frame on top at this moment is always the one that's executing right now. The ones underneath it are frozen, waiting for the ones on top to finish. And when a method finishes executing, its stack frame is erased from the top of the stack. And when a stack frame is erased, its local variables and parameters are erased with it. You can never access those local variables directly again. So if there's anything you want to save, you'd better store it in an object or return it to the calling method. And I want to point out that the java.lang library has a method that's really useful for debugging sometimes called thread.dumpStack. Which just prints a list of all the methods that are currently on the stack, and it doesn't print their local variables, unfortunately. It does usually print the line number you're at within each method at that moment. You've already kind of seen the output of this method, because whenever the Java virtual machine throws an exception and crashes your program, it does this automatically. But you can do it even when your program's not crashing if you want to. It can help you find bugs sometimes. Like, especially if you're trying to find out which method is calling another method with illegal parameters, for instance. Question? I am going to devote the whole last half of this lecture to that question. How does recursion work with a stack? So I'll give you an example soon. Before I do, though, I need to talk about parameter passing, and then we'll come back to how the stack does recursion. So, as in Scheme, Java passes all parameters by value. Now, the phrase pass by value is official computer science jargon with a very specific meaning. It means that when you pass parameters to a method, that the actual arguments are copied into the formal parameters. You're not changing the original. This is different from some languages. Some languages allow you more than one way to pass parameters. You can pass by value, you can pass by reference in C, for instance, or at least in C++. Here you can't pass by reference. You can only pass by value. So when you pass by value, you get a copy in your local stack frame. Changing that copy won't change the original. To demonstrate that, you have some code in the handout that I've made available that, let's start with this method called doNothing in the intBox class. So an int box is just an object that's designed to store one int. And what I want you to imagine is that there's some other class somewhere else that has a method in it that executes the following method call. First, it declares a variable that sets a equal to 1. And so I'm going to draw the stack on the right-hand side now. There is a stack frame for the calling method. Let's suppose it's the main method. And in that stack frame, there's a variable called a, and I store in that variable the number 1. And let's suppose now I call doNothing on a. And my goal here is I would like to set a to 2 instead of 1. Will the doNothing method do that? Well, here's what happens. We call the doNothing method. It gets its own stack frame. It has a parameter called x. And because we always do pass by value, we copy this 1 from the box A into the box x when we call doNothing on A. So now I have my number 1 is copied into the box x. The doNothing method does one thing. It sets x equal to 2, erasing the original value of that parameter. So that 1, bye-bye, you're now a 2. Now the doNothing method is finished. So when Java finishes executing a method, it erases its stack frame from the stack forever. And now we come back to the original main method, and the main method can continue to run. And you'll notice that a is still equal to 1. The doNothing method, as befits its name, did nothing of importance. Whatever it did do is now erased. So you cannot change the original variable a by changing the parameter that you've passed in the doNothing method. Sometimes you want to be able to pass information that can be changed so that the called method can communicate information back to the calling method. This is the wrong way to do that. What's the right way to do that? There's several. One's the return statement, of course. But another one that's interesting is to have an object that you store the information in, and you use that object as a way of communicating that information back and forth between the two methods. And so that is what the second example here does. The idea now is that when the parameter is a reference, the reference is copied, but the object is shared. So let's see how that works. I'm going to now divide a little bit of my space here into both a stack on the left and a heap on the right. And I'm going to suppose that, once again, we have some code in a main method of some other class somewhere that looks like this. First, it constructs an int box. So in the main method, we declare a reference variable called b, and that will be stored on the stack here in the stack frame for the main method. We construct a new int box object, which is essentially empty or contains a 0, and that gets constructed on the heap. And that has a variable I, which we haven't initialized yet, so it contains a 0. And now, but I really want to use this int box as a way of communicating information from the called method to the calling method. So now let's call this method set3 here. So I call set3 with the parameter b. The Java virtual machine creates a new stack frame for the set3 method that I have called. The int box that I passed in is copied to a variable called ib. So Java is using pass by value, which means we're going to copy the contents of this box into the ib box. So b and ib are not the same box. They're two different boxes that happen to point to the same object, but they do point to the same object. So if I change that object, both the caller and the callee can see the changes. So now we execute one line of code inside the set3 method, and that sets ib.I equal to 3. In other words, it writes a 3 into this box. Now the method has finished executing, so we can, so Java erases set3's stack frame because it's over. Nevertheless, now the main method can still see the change that was made by the set3 method because it was made in an object that we're both pointing at instead of trying to change the passed parameter itself. I have one more example, which is very similar to this one, but this example is meant to show you a common programming error. And this is a programming error that some of you have already experienced while trying to do homework 3. Now we have, again, a bad set4 method, which is very similar to set3, with one difference. It makes the mistake of trying to construct a new object and replace the old object with the new object. Seems like a good idea, but it doesn't actually work. At least it doesn't succeed in communicating information back. So once again, stack on the left, heap on the right. Let's suppose we have the same setup we had before. The main method constructs an int box. But then instead of calling set3, we call bad set4. In the main method. So Java creates a new stack frame for bad set4. And the variable b gets copied to ib, so b and ib both point to the same object. So far, so good, but now I make a terrible mistake. I try to replace that int box with a brand new int box to store my new number in. So what happens is now bad set 4 is constructing a brand new int box object and replacing the reference to the old one with a reference to the new one. So now IB points to this brand new object, and we store 4 in that object. Now the bad set 4 method is done, so Java erases its stack frame. And has bad set 4 succeeded in communicating the number 4 back to the main method? No, it hasn't, because the main method still has the original box. That box that has the 4 in it isn't actually accessible. There's no reference pointing to it at all from anywhere, so it's not going to do any good, and it's going to get garbage collected. The similar problem that comes up in homework 3 is some of you tried to take the input array and replace it with a new array. You can't do that. You have to make the changes in the original array that you're given. Are there questions about this? Mm-hmm. These are neither compiler errors nor runtime errors. They're logical errors. So your code's going to compile, it's going to run, it's not going to blow up or throw an exception, it's just not going to do the right thing. And that means it's even harder to debug. Yes? Mm-hmm. A component of an array. If you are changing a component of an array, then it's a lot like the second example I gave, the set3 example. The only difference is if instead of using an int box, you use an array, so this could be an array of 4 ints, and the set3 method maybe writes 3s into those array elements, then yes, that will work, and the calling method will see those changes to the array. Mm-hmm. So array, int box, doesn't really make a difference. Works both ways. Other questions? All right, by request, we can now talk about recursion and how that affects stack frames. And while doing that, I also want to give you a useful algorithm, too, that uses recursion and stack frames in an interesting way. So we're going to talk about binary search. Now, when a method calls itself recursively, what that means is that the Java virtual machine will create 2 or more stack frames for the same method. If a method calls itself and then calls itself and then calls itself and then calls itself, well, that's 4 stack frames for the same method, 1 for each call that's currently in progress. But only the top one can be accessed at this instant in time. So to demonstrate that, we're going to look at a recursive binary search method that searches a sorted array of ints and is searching to find out if there's a particular int, like, is the number 3 in this sorted array? So I'm going to look for a particular value. I'm going to call that value find me. If we find it, then we want to return its array index. If we don't find it, if it's not in the array at all, then we're going to return a constant that we'll call failure. And this constant tells us that we did not find the item in the array. The easiest thing to do is just walk through the array from left to right and check every item in the array, every int, to see if it matches find me. But that's slow because you have to go through the whole array. Because the array is sorted, there's something much faster we can do. And the idea is that we're going to start by checking the middle element of the array first. If find me is less than the middle element of the array, we only have to search the left half of the array. If find me is greater than the middle element, we only have to search the right half of the array. And having cut the number of possibilities in half, now we repeat that idea over again with half the array. We divide it into 2 quarter arrays, and we decide which one of those holds find me. And then we go down to 1/8 of an array and so forth. So to give an example, let's suppose that we are searching for the number 1 in the following array. -3, -2, 0, 0, 1, 5, 5. So we always start at the middle. Here is the middle element. If it's an even number of items in the array, then there are sort of 2 middle elements, and it doesn't really matter which one you go with. But we're going to compare this first. We compare 0 with 1. And find me, 1, is greater than 0, so that means that the thing we're looking for has to be in the right half of the array. And so now we're going to recurse on the right half of the array. And so we do it again. We look at the middle element. We compare that 5 with find me, which is 1. Find me is less than 5, so now we have to search in the left half of this array. So we've narrowed it down to just 1 element we have to look at now. And we check that 1 element, and we've got a match, so we return 4, which is the index of that element. So that's the high-level idea. Let's boil this down to some code. To do that, we need to first figure out what the base cases of the recursion are. And it turns out this recursion has not one